Hey, y'all, it's Dr. Know-It-All. I am with Dr. Scott Walter coming to us from the upper Midwest from Michigan this morning. And we are going to live stream a discussion about EVANNEX and their new robot, Neo, who is not a guy in a suit. Let's start with that thing first, guys. Anyway, welcome, Scott. It's been a little while, actually, because you were in Iceland and I was very jealous and I was starting school. So we've been busy and it's nice to have you back on the channel.
Yeah, I was also in Norway just before getting to Iceland. So
Oh, nice. Okay.
yeah, I got to see and got to experience let's say, really cold end of summer in Iceland.
There we go. So
having to dress warm, but it was right there.
That's awesome. I just was thinking this is Labor Day weekend, and there's a little bit of irony that we've got a labor robot here, that's going to be potentially in the home. First things first, let's go ahead and play back this video, which is a teaser. Jason Carmack. Yeah. Anyway, they did a very lovely, 45-minute interview with
no, I think it was about 18 minutes.
18 minutes. Sorry. There's another one coming out today. Yeah, that's what it is.
Right. It's part of the S3 season 2.
Yeah, exactly.
Documentaries that he does weekly on startups, and definitely worth listening to, as well as the spaces that was out yesterday after the release of it to kind of talk a little bit about it.
Right. I'll put links. I forgot to put that in right now, but I'll put it in after I finish recording this, or if I think about it while we're doing it. But I'll definitely put in the spaces. It's quite excellent, and Bernd is very okay. Anyway, Bernd is really open and it's great. It's a wonderful space. They admitted to being afraid of Scott, so I thought that was the best part of the entire thing. So yeah, without further ado, let's go ahead and let people who haven't seen this see this. So this is a quick intro that was done by S3 for the robot, and there is music underneath this. I'm going to turn it off for copyright strike issues, but there's no actual voices. So
yeah, there is some sound in there, and I think the music they use might be kind of public domain music, because I've heard it in a lot of other things. But yeah. You never know. So anyone that you should be able to find this teaser somewhere, because there is sound.
Yes. And I'll just turn it on for a second, because it's very I think it is worthy of. Yeah. So just for that, you can hear that kind of like whatever mechanical.
You can they had to turn up the sensitivity on their mics to pick it up, because that's the first thing I noticed in the video is like, oh, there's something missing here, and that is the sound. And not that they cut the sound, it's just that the bot is very, very quiet, and we'll talk about the importance of that a little bit later on. Is something that Bernd kind of discusses a little bit. That's very key to why they're able to accomplish what they're able to with what appears to be so little.
Right. And let me just hop through so we have another view of EVANNEX.
And okay, of course, so we got some.
We're going to talk a lot about the hands. I'm sure we will definitely do that.
Yeah, we're going to because that's like the only thing we've been able to see. Everything else is kind of hidden, and even then, they blurred some of the images to make sure that we could not get really a close up.
It was not we, it was you. That's what I said. They said that they were afraid, and they actually blurred it out because of Scott Walter. So there you go. You are a holy terror.
I think just in general, there are other clever people out there as well. So don't worry.
Well, anyway, that's what I heard. I was listening. So anyway, okay. So number one, one of the things you said was you were quiet on the spaces, and you said I'm speechless, and you said that's very rare for me. So explain why this discussion about Neo left you speechless.
Okay, so I mean, the first thing is let's just go back to the teaser, and that's sort of the setup to the question that I had for him, and that everyone that watched the teaser had a very similar impression. So this is why I'm going to turn around. Is like, what was your impression when you looked at the video?
It was okay. So this is a funny thing, but when I saw it, I immediately was like, oh, wow, really, really good. And then I reposted it and said, this is amazing, because it'll be in the home. And we're going to talk about that too. Right. That's a really important part. I said, this is amazing. It's in the home. And then someone said, there's a rumor that this is a guy in a suit instead. And I I was out and about yesterday and I wasn't able to participate in this stuff. I was at Ikea actually at the time. And I looked and I was like, I said, oh, I can't guarantee absolutely that this isn't a guy in a suit. So it gave me some pause. So I think my reaction is this was fluid enough, human enough that I could believe that it actually could be a guy in a suit.
So basically it passed the humanoid Turing test, which is it's so good people are convinced it's fake.
Right.
And that has not really upset anyone at 1X. They've actually seen that as a compliment. That when that is the actual reaction, that means you're doing something good. So they're like, fine, because we know it's not fake. And one of the reasons we know it's not is if you look closely at the hands, it's not a guy in a suit, because we get enough of the close up of the hands. Those are not gloves that are being worn on there and everything else. And we've seen enough of 1X. We know enough about them. It's not like a company that just came out of nowhere all of a sudden. They've been around since 2015 working on this. They have Eve, everything else. So they have a legacy that we know on. We've listened to Bernd in many podcasts before. He's very articulate. He really knows his stuff. He's got the passion, everything, and everything he says makes sense. Everything passes the smell test without a doubt. So most people, it was so fluid that it was just convincingly, it just looked very human-like, and that is because the motions are all very integrated. The whole body, the legs, everything is kind of like part of the motion that's there. Now, that's not what struck me. What struck me was like a really fine nuance, which was the question that I asked Bernd, and that is the robot seemed empathetic. It was kind of aware of the situation and was able to kind of read body language in context. So it's sort of reading the fact that she's tying her shoes, which is like an indicator she must be getting ready to go somewhere. And there's a backpack sitting down there, and the robot is like, oh, maybe I could be helpful here. And then I believe the bot is able to hear sound, but maybe not able to speak because it's speechless, like I was left. So I had to revert to some simple kind of body language and hand signs to be able to say that, oh, do you want this? And then she indicates yes. And I'm pretty sure probably understood the yes, or at least, again, her body language of what was going on, and goes ahead and grabs that. And I was just wondering, it's like, okay, is that something, because a lot of people say, well, it was scripted, it was a teleoperator or something like that. It's like, but they've been doing a lot in the AI space for a while. Remember, they have also investment from OpenAI. Bernd knows Sam Altman, for a while and everything else. So, it's quite possible that was an emergent behavior. And Bernd said yes. He could not go into the details. He says there's some more exciting things in here, but they've done a lot of this kind of training. That's all it is they're training in the house and everything else, where that's one of those things that the bot's going to be starting to pick up. And he's saying that definitely you don't have to ask the bot for help. The bot is just one of those, I guess you could say almost busybodies that's looking around how to be helpful. And as soon as it kind of notices something, say, oh, I think I can come in and help this person do this and that. So it seems to be kind of, maybe a trained behavior in a way, but also a little bit of emergence is going on there. So I was very, kind of careful. It's like, okay, I'm seeing that. That's a very strong indication, but I need kind of confirmation that is really what was going on. So I was a bit, actually, I was hoping to hear that answer from Bernd, and I guess I was really shocked when he went in and confirmed that that's really what's going on. And we see in the kitchen example, the same thing was going on, that the bot's being helpful, handing the eggs over. And I'm not sure that the cook was necessarily saying, oh, I need some more eggs. It was like, oh, here, do you want to, just kept on handing them. And so those are some of the subtleties that we want to be looking at in here. What was your take? Did you notice that as well?
I did. I think the teleoperation made me wonder about the quality of that part, because the teleoperator could have been operating it in that sense. It was really fascinating listening to all of that. So to be clear, Bert said there was a guy off stage operating the robot at this, but that Eve, the previous robot that is basically like this, except the hands are not as dexterous and it's on wheels as opposed to legs, is not that she's actually pretty much end. I mean, she is end to end, but most of the behaviors that they show are actually AI driven. So he actually specifically said that when you see the actual trained robot as opposed to the teleoperator, it's actually smoother. That was an interesting.
It's much better.
Yeah.
And that makes sense because teleoperation is very difficult. You cannot be as fluid and as fast as you would like to be because there's the lag. You're not really there. You don't have quite the full sense of presence. You know, all those things there that you know, just kind of make it difficult. And so they put a lot of effort in making the teleoperating experience seem more and more like true embodiment of what's going on. So you really, so the vision is very good. The lag, I mean, you talk about all kinds of lag. First, you know, what you see in getting into the headset, that has to be really fast. But at the same time, your responses and your movement have to be very quick, and then you have to be able to see that very quick, and you have to do it in very quick order. And I've played around with VR headsets and stuff like that, and been able to get that also as well with mannequins. And it's a little bit frustrating if it's a little bit laggy. It's hard to get it absolutely perfect. So you do have to put a lot of effort in to get it. But it makes sense to me that you get enough training data. And I think he says, like, once you get like about 50 sets, you don't improve. There's no improvement at that point. That's about all you need to capture. And then it would make sense that the trained data will then means it's going to actually be a lot better when it goes ahead and references whatever those motions are and be better at it. I think he talked about that. There may still be a little bit of cleanup that you would try to do to get it to optimize, but it seems to be doing it by itself.
Yeah. I think another really fascinating thing, and this was kind of like, this was a little bit of a jaw dropper moment for me, and I don't know why I hadn't thought of it, but he said when these robots, like, let's say, you know, you have 100,000 of these in people's houses around the world, when they're not actively doing something, like, you know, you go to work or something and it's just sitting there at home alone, rather than just sitting and doing nothing, it could experiment with the world and learn. And that it could utilize that time when it's not doing specific tasks for you to get generally better. And I was like, oh, that's really cool. You know, I don't know why I hadn't thought of it myself earlier, but it's like, yeah, there's a lot of downtime around the house.
Now the question is whether that's going to be the type of things that they prompt or whether the robot comes up with the experiments itself. And the other thing is how much of those experiments goes directly into training right there. Does that bot suddenly become smarter, or is just one of those things that the information has to be uploaded and then you have to go ahead and do all the back propagation, everything else again? What's your feeling? I mean, I imagine by using transformers, you can get maybe a little bit of kind of local knowledge, that you might get a little bit of wisdom that's right there, but it's going to be latent, right? Or it's going to disappear after a while. So it's not going to be permanent.
This is, this is actually a huge, I mean, what you touch on is actually, I think, the major question for embodied AI. And that is, how do you create local domains of knowledge? And not just embodied, but also chatbots and things like that. But we have now retrieval augmented generation, or RAG, for LLMs, and that allows them to access a database. So let's say that the LLM was trained up to January 1st of 2024, right? So it's missing 8 months or so of data. But what it can do is it can access, if there's a big pool of data out there that somebody has like taken and embedded the internet or whatever particular domain you're talking about over the last 8 months, it can then go out and search that for essentially it's kind of k-means clustering. It's I mean, it's kind of it's actually old school AI. It's actually taking a vector embedding of the world of whatever information, and it's using the same vector embedding of the question, the query, and then it's doing k-means clustering. It's just going, what vector is similar to the question that was just asked? And that is much more robust than a string match, right? Because you can go into Google and you can say, I don't know, Andre Karpathy, CVPR 2023 or something like that. And they're using that kind of AI because that means you don't have to have the exact string match. It doesn't have to have those 4 words in that order to find it. So this is around, and this is kind of classical AI, and it's really fast. So I could see something like that where it has some RAG ability to be able to go out and search for local domains of knowledge that are since the last training run. Possibly. It also, but in embodied AI, it becomes a much more dangerous sort of scenario. And I want to touch on that next, which is exactly why I have this picture up. But I think that the safe way to do it is for it to collect data, upload it to the mothership. They do all the retraining and things like that, and then they download a new version, which is exactly the way Tesla's FSD works right now. And it's entirely
that's the thing.
Yeah, it's entirely for safety.
Right.
So let's talk about safety, because go ahead. Yeah, go ahead.
Yeah, and the other thing is, remember, with Tesla FSD, they can kind of query certain edge cases that they're looking for. Right. And I'm just wondering if it'd be the same thing. Is that okay? We everyone that's in the kitchen of this style, this is the kind of experiments we'd like you to do right now. We're looking for that. So maybe prompting it to do certain things during that idle time, and then uploading it.
Yeah. And then certainly any kind of problems, like if the bot falls over or something, it should hopefully flag that and upload that to the cloud, so that it's like, okay, why did it fall over? It tripped over a wire that was there, like somebody's vacuum cleaner cable was there and it tripped, whatever that is, that it would then find that and be able to retrain for the future to look out for vacuum cleaner cables that are there on the ground. So let's talk about safety.
Right. And that would be the other thing, as far that also be mapping the house, is that, every house has got these trip hazards everywhere.
Yeah.
And if you're not familiar with the house, you're going to trip over it again and again. And we kind of learn that's like, oh, when you go into that room, you've got to be very careful. There's something there, the carpet slips or moves or something like that. And so to me, that seems like that would be local information you have to have. You don't need to upload that to the cloud. You just need to say, all right, when we're walking around here, this is how you have to be careful. And that's going to be interesting for local embedding to really understand what's going on. I'd love to see that for FSD, the ideal way to drive in and out of my neighborhood.
Yeah. And for me, I always take a back road around the back end of the mall instead of the main road. And to this day, the navigation system is too clueless to figure out that, even though literally 100% of the time I go this way, it's like, it's too stupid to figure out so I always have to disengage full self-driving to make that turn. So that the question is, how do you create that local knowledge pocket? LLMs could be potentially the way to do it, because they could store it in a sort of a narrative sort of flow. It's something that I would love to ask Bernd about, if he would be willing to talk about it at some point, is how do they do that kind of thing? But it's critical, because you're right. You don't need to upload where is the couch in this particular house to the cloud. That's just local knowledge that it needs to know personally, but not every other bot in the universe.
Right. And you have to be aware of that there are going to be certain items in the house which are fixed, and others that could move around, like the flower pot. It's kind of always there, but it might move a little bit. And sometimes it might move in a way that it gets, it's going to cause you to trip because it gets moved out 6 inches when before you weren't aware of it being there.
Right. So, where is okay. So anyway, I've been wanting to get to this because I think this is a really important point. This is specifically built, and this is a very different strategy than pretty much everybody else that we talked to, who's all like going in the factory first, going to have a controlled environment. 1X, Bernd is very clear about the fact that he wants this to be consumer facing, and that has some major downstream consequences. The first is, and the reason I'm on this picture here, still frame, is because they're hugging. And that is a specific cobot sort of thing. That's not something you would probably want to do with Optimus or Figure 1 or Figure 2, or the other robots at this point, because I don't know that they're designed to be safe enough to be around humans yet. So
they're not certified. They're currently, when they are doing a lot of the jobs in the factory, there's a standoff distance. The humans are not allowed to get that close because they do not have the certification.
Right. And they're made out of, metallic or hard plastic or something like that. So we have a very different look to Neo here, and also to Eve, to be fair. I mean, they were obviously working on that. And when we talked to Bernd several months ago, he talked about how Eve, the problem with Eve was, number one, it's on wheels, and so it's not quite flexible enough to be able to be utilized everywhere. But number two, it was never designed to be mass manufactured. It was just they were proving out the technology, whereas Neo is designed to be mass manufactured. So anyway, this is not brand new. This is stuff they've been working on for quite a while. But so first of all, number one, let's go with the weight. Why? It's 30 kilos, right? It's just nothing.
30 kilos.
Yeah.
Yes, that's absolutely nothing. So for context, I think Optimus is supposed to be
like
about
70,
55 kilograms, I think.
Yeah, and I'm about.
I'm not 75? Sure that.
Is that right?
Yeah, I'm not sure that it actually is 50, Optimus, because a lot of these numbers you see are kind of aspirational. We haven't had confirmation. So they're somewhere in the order of, 40, 50 to 60 kilograms. A couple of Chinese bots are a little bit lighter, but some is like the Hobbit size one that's very, very small. And some of the others that are tall and also only about 45 kilograms, but they have, very small battery packs and they don't have hands yet. It's like once you start putting that in, you're going to be adding a little bit more. So most of them are really in the order of 50 kilograms or more. So 30 kilograms is remarkable. And there's several ways that they're getting there. One of them is just the actuation strategy, that the fact that they're using these tendon drives, but more importantly, that their motors are very high torque, but they don't have gearboxes. Getting rid of the harmonic drives, getting rid of that. So that means your actuator mass is a lot less. Because actuator mass is a lot less, you can make the bot a little bit lighter. And if the bot's a little bit lighter, that means your torques don't have to be as high, right? I mean, it's kind of like the rocket equation that, is that as you start to do that, you get these improvements. But the other thing is the development of these drives, they're so power efficient, you don't need as big a battery pack. Now, the thing that shocked me is that what consumes the most power in Neo is the inference chip. The actuators are actually less. That's the opposite of everyone else. Everyone else, they need a lot more power and going to the actuator. So they need to be running sometimes between 250 watts to 500 watts. It seems like Neo overall is able to run maybe around 100 watts, 150 or something like that max. So all of them are having to burn the same amount of energy in their inference, no doubt about it. No one's got the secret sauce to have a fraction of that. But because their actuators are so efficient, they're not using anything, which means his battery pack is pretty small, yet he's still able to get 2 to 4 hours out of it.
Did he say 500 watt hours? Is that what he said?
No, yes, 500 watt hours. So that means basically 1/5 the size of the Optimus battery pack. Now, Optimus is designed to go 8 hours, could go 8 hours, but if you're pushing it to its limit, it's more like 4. So you're looking at Neo 2 to 4, which means probably if you're really pushing to its limits or something like that, making it do a lot of work, maybe you're only getting 4 hours. But they've already looked at the use cases, and it's not like in the factory that you have to have it run, make it through an 8-hour shift necessarily. It's like in the home, all you need is like 90 minutes or so of work out of it. And if it sits down for 15, 20 minutes to get a recharge before doing something else, that's fine. That's fully acceptable, especially when it's light. So making it light is very important, no matter what material it's made out of. Being hit with something that's 30 kilograms still hurts a little bit, but it hurts a lot less than getting hit by something that's 50 kilograms. So that's the first thing, bringing the mass down. And then all the other things that you have to do. And and it just kind of seems like the snowball that every single little design decision they make to do something gives them benefits somewhere else. So a lot of times to get high torque and everything, you have to do it through gearing. And these harmonic drives and everything like that. And harmonic drives are a way to get rid of backlash. And the way that they get rid of the backlash is like, in a way, you're almost making these gears that are intentionally kind of out of sync with one another, that they're always grinding and they're always like locked in place, so you can't get that backlash. And that's why when you run those systems, you hear sound. Now, when you hear noise is a form of what? Energy.
Noise,
right?
Yeah, it's there's electric noise and acoustic noise, but either way,
So basically, if you're hearing it, that means there is energy being dissipated. That means you are generating this thing, through a variety of things. It's telling you there's friction, it's telling you there's drag, it's telling you there's loss. So the louder your motor is, the less efficient it is. The more quiet your motor is, the more efficient it is. And so by getting rid of the gearbox, which gets rid of mass, you get rid of a lot of the other losses that are kind of going on in there. And that's why they focus very much on direct drive and figuring out how to get a very high torque kind of motor in there. And the other thing is gearboxes are really difficult to back drive. I mean, it's like
Yeah.
You're fighting against this ratio. And that is one of the safety hazards. If you don't have something that's back drivable, that's why cobots want to be back drivable, because that way you can't get pinched.
Can you for those who don't know, Scott, can you just, what is backdrive? Just for those who might not know.
Oh, that means, if I'm actuated with a motor and I come in like this, and I turn it off or something like that, and I try pushing on it, it won't move.
Yeah.
And so to be able to backdrive, it means if I apply enough torque or enough force against it, that it will go the opposite direction as opposed to locking in. And this is a problem with high gear ratio transmission systems.
Right.
Is that if you get pinched, you can't push it out of the way. And this has actually caused a lot of factory floor deaths with robots. It wasn't getting hit by the robot. It was actually getting pinched by the robot, or pinned in some cases, that a robot moving back in a worker getting caught between the wall and the robot, and not being able to push back. And then the robot sensing there's something out and turning itself off and initiating its brakes. And it's like, oh, they can't do it. And then everyone else scrambling in, trying to figure out how to get the robot up and down. And then it's too late. So the whole idea is you want to do it. Now, the other problem is that an industrial robot is literally bolted to the ground.
Yes.
So when you're pushing against it,
it's not going anywhere.
Push the arm. It's not falling over.
Yeah.
This thing, if it pushes you against the wall, you just push back and it's going to fall over. So you don't have to worry about that part. But the main thing is, like, if you put your arm between here and it does this really quickly, what's that going to do? And that you can definitely get injured if you in a large pinch point like that. So you try to get rid of like the normal pinch points where you get your finger in there and it's like, ouch, kind of thing. But then you still have these larger kind of pincers that can kind of come in there. So a couple ways you can do that is that, like, the human arm is like, I don't know of any human that can actually bring that all the way down to 0 degrees,
Right.
It's pretty hard to do that.
Yeah.
So you also design the hard stops in your robot to make sure, look, the human range of motion is not, from 0 to 180 degrees here. It's like 0 to 135 or something like that. That's going to eliminate the chance that this is going to be a nutcracker, right? That, so you're not going to put walnuts in there and start cracking them. So that's one thing that you want to try to eliminate. And then, of course, any potential pinch points, you soften them up by putting covers and everything else to make sure you're not going to be hurt.
Which again is why we have clothes. It has a suit on. I wanted to pause this video. I'm going to keep playing it here, but I wanted to pause this because this wrist right here, they blurred it out. That's for you.
They blurred it out. Yes.
So, anyway.
Now I can intuit a little bit of what's going on. You can see the yaw motion that's going on there. If you go back there, you can kind of see yawing. So the wrist is a cardan joint. We can kind of see it. The wrist is yawing, and there is like one image in the teaser. So they didn't blur anything in the teaser video, and there is kind of a close up in the teaser where you can see a little bit when you blow it up on there, and that you can see the 2 axes of rotation that you have.
Right.
So it's basically okay, like right about there. It's going to stop it right there. If you zoom in, you're going to see on the top part of the hand this thing that's kind of poking out. That's what's allowing you to do this yaw motion. And then you can also see there's something perpendicular to it, which is the wrist motion right there. So they have a pin joint there, another pin joint there. Now, the big, I wasn't surprised at it because it's basically the same that the Tesla wrist has. However, all the other wrists don't do something like that in the humanoid bots because they've all decided to make their joints actually an actuator. And that's why they have these big bulky wrists. You get one after another, and the question is, how do you make 2 motors intersect like that? You can't. That's why you'd like to build a joint and then somehow actuate it with motors that are distanced in a way. So in a sense, what we're seeing here, and we'll get into a little bit, is that this hand is great.
Yeah.
And what we're seeing is probably what the Tesla 22-degree freedom hand is going to look like.
Interesting. Yeah.
But
okay.
There still is going to have like a lot of interest. So the question is, how are they actuating the movement of that? And I think the answer is pretty clear. They're using tendons, because they keep on talking about tendon drives. They're not suddenly going to use a different strategy there. So that's kind of how it's being actuated. And that's the kind of motion you want to have. The other idea of putting an actuator on there is stupid because that's not the way the human hand is done. If you want to go to biomimicry, the other thing is a lot of times when they put those actuators on there, they're either displaced back. So there was one Chinese bot that came out recently that I had a pretty harsh review on it because the pitch motor was so far back in a line in such a way, the arm looked like it had two elbows as opposed to an elbow with a wrist down there. And it's like, that doesn't work. The idea that my wrist is actually should be rotating back here. And, but because they had the yaw motor down there, and it's a big, heavy actuator, which means you have to carry that mass around. There's a mass that's going to bump into things. It's very bulky. So again, when you try to reach into a tight place, suddenly you're going to get resistance, or you're going to bump into something. But it gives them this advantage that the yaw axis can go more than the plus or minus 30 degrees that a human can do. They can go like plus or minus 90 degrees or 120. And they see that as some kind of advantage. It's like, I see that as no advantage whatsoever, just because the hand can flip around and do weird things. The same thing with this action. You don't have to have it. Now, when you go to that cardon joint and the actuation they're going to have on there, the limits of motion they're going to have is going to be very similar to a human hand, which is very good because if you need to do teleoperation, and the idea is, and that's for training, the teleoperation for training is you need to be as close as possible to human capabilities. So you can get that one-to-one mapping. But if your robot suddenly has hyperextension on the elbow and is able to do like weird things with the hands, you can't teach it. Okay, you can't teach it telerobotically. So what's the point of doing it that way? So that's a very good way. Now, what they're probably hiding in the wrist is not the fact that they probably have some cables or something to be able to actuate it, because anyone that sees it can probably sit down and figure that out. What's probably important is, remember, they've got all these fingers that are moving. And what's making those fingers move? Tendons, right?
Yeah, tendons.
And where's the actuation for that?
That's the whole cleverness of their system, right? Mostly.
It's way back here. Now the tendons have to run through that wrist.
Right.
So you literally have to have a carpal tunnel in there for these things to go through. So, how they are mastering and doing that and going in there, that's probably some of the IP that they like to protect, and why they wouldn't want someone like me or someone else to look at it. But we can make some observations about the hand. So they went from, with Eve, they just had the two pinchers. They're actually using an off-the-shelf gripper from Robotics out of Quebec. For that, to go from using that there, which we see that was the Robotics gripper, to what is, like I said, hands down the best hands in the business right now.
Right.
There may be, there may be a couple of benchtop hands that people have kind of worked on, like, remember the OpenAI one with the Rubik's Cube. I don't know whether that's necessarily better or not. The thing is, it has to be a hand that is able to be actually put onto a humanoid arm and function. Okay. They don't count. So the only hands that are counting are hands that we are actually seeing on a humanoid bot. We've got a lot of degrees of freedom, and we can see a lot. So I think Bernta said it's 20 degrees of freedom, but we got to be very careful in the apples and oranges and how we compare degrees of freedom and what's being counted and what's not being counted. He's not counting the wrist in that. That's the fingers. And we can tell because he's got all the knuckles. Right. And he's actually got all the knuckles in the thumb. Yes. So it's not a two-knuckle thumb, which the Tesla bot is probably going to be. It's three. And it has both the clenching or flexion and the abduction, or kind of displaying capability there. So, which means each digit has 4 degrees of freedom. Right. We've got 5 in there. That's the 20 we're talking about. If we do that comparison with the 22 DOF hand that Tesla's coming up with, they're really 19 because they're including the wrist in there. So if you want to make them the same, that means we're looking at a 23 DOF hand. The other thing we're looking at is all the digits are different lengths. They are the same lengths as you would typically see in a human hand. Right. I'm assuming the Tesla one is probably also going to have different finger lengths now. Just about everyone else is still doing the same finger lengths. So either doing 2 knuckles, some of them are 3, but everything's the same with a little bit of an offset. They've decided to go all in and say, no, we're going to really make it so it looks very much like a human hand. Right. The other thing is, look how thin the palm is. Exactly. So some of the other hands that are out there are very thick before you even get to the wrist. Yeah. Which is a nightmare. And that's there. And it's integrated enough in the hand that I would go ahead and call it actually a 23 DOF hand, because I'm pretty sure the wrist and everything, everything kind of goes back here. All the actuation is back there. So it really is like a full lower arm. Right. Right. From what Bernta said, it sounds like, the actuators are throughout the system close to where they need to be.
Yeah.
So he does talk about there kind of being muscles here in the forearm, and some muscles up here. So it seems like he's got some actuators up here that to make the elbow move. Now, see, again, this is how you can kind of, where you assign degrees of freedom is that typically, you know, we think of in robotics that the wrist has 3 degrees of freedom in the wrist and the elbow has 1 degree of freedom. Right. But if you look at the movement of your arm, you kind of know, so wait a minute, this rolling movement kind of looks like it starts up around here. And depending on how you build your robot, I mean, just about every robot arm, it really does rotate kind of about here. So it's almost like it's a 2nd degree of freedom down by the elbow. Mm-hmm. So you can almost consider the elbow as having 2 DOFs there and two needs to be actuated. And that's what Barrett's saying is like, they've got a muscle up here, the upper arm, which is responsible for these 2 movements down here. So this takes care of that. And then the rest of it is taking care of that. What I would like to know, and, you know, we can see they can do this, is whether they can individually move each other. You know, again, the Vulcan live long and prosper symbol, whether that can be done. We know there's the motion, but I haven't seen enough to be able to tell whether there's independent control or not, because that would mean either they have 7 actuators dealing with a hand, or I think you would have to have at least 10 at that point. And the reason is, as a thumb definitely has an individual motion there. So we're really just talking about the 4 fingers and then being able to do this. So that will be interesting to know a little bit about that and how much control they have there. But it's a beautiful hand because it is just so human-like and so thin. And I would say, it tops the others. You know, the 2nd place probably goes to Sanctuary now, and maybe Clone, but Clone doesn't have, you know, a full humanoid bot yet. And in both cases, both, you know, Sanctuary and Clone, they're using hydraulics for the actuation.
And this is not.
Which means they're very loud and it requires a lot of power to be able to do that. So you can get a lot of finger strength and grip strength and everything else out of it, but you can't. Now, despite being tendon controlled, now everyone's hand is at some level tendon controlled. It's just a question of the length of the tendons. So everyone that has put some sort of actuator in there, you know, they are pulling on a cable, which is what is making it do that. And it's a question of like, well, it's when you put it back behind the wrist, then does it become tendons? I don't know. What do you want to call it that?
Well, there are other it's pretty obvious that Tesla's next version of Optimus is going to have tendon control, because Elon's pretty much said that they're moving.
He said that. So they may still have an actuator in the hand, because he said something just for the thumb. Most of them are going to go back there. Maybe they're still going to have something for the thumb, but I'm almost just wondering, why not just go ahead and put it all back there? But we'll see.
So the hands are really amazing. The body, you know, and Bert, I love that he busts out the high school physics all the time, and he's like, energy is you know, proportional to the velocity squared, and so he's always like, how fast is that motor spinning? How fast is that joint moving? How heavy is that thing? Because it's also proportional to mass as well. So. So you know, so he talks a lot about this, and I noticed that he's very stuck on this idea, and not stuck for a bad reason, but for a good reason, and that is that their robot can move faster because it's lighter, because their motors are not turning as rapidly, because they're not gearing them down. There's a whole bunch of advantages that you get when you go to this more tendon-based system over direct drive with geared down. Exactly. And you know, if you look at a lot of the industrial robots that are out there, they may have joint speeds of like, you know, 90 degrees per second or 120 degrees per second or something like that. Yet they're geared through their servo drives, and their servo drives are able to go like, you know, 2,500 RPM or something like that. So they can go very, very fast, and of course they're very big. So you get this big, massive coil rotor in there. That is rotating, you know, maybe 100 times faster than the actual movement that you're going on there. And this is Barron's point. So what that means is that the rotational kinetic energy of that motor, when you compare the two, is 10,000 times more. Exactly.
Which means when you have to suddenly stop, you have a lot more energy that has to go in to try to stop that thing to come to a complete rest. And as he talked about that, you know, we know that you know, traffic fatalities that, you know, go as a square of the speed of being hit. So, you know, being hit at 10 miles per hour versus 20 miles per hour, there's 4 times greater chance of injury, even though it's only twice the speed, because energy goes to the square, because everyone remembers kinetic energy is 1/2 mv squared. So when you start doing that with velocity, and then your power requirements are going to go up and everything else. And because of that, there's this caution that you need to have. The other thing he points out is this idea of torque transparency for the reinforcement learning to be able to do it. That if you have things highly geared, it's more difficult to get the torque transparency that you need for the end-to-end control of your system. And that is his feeling on why the Chinese bots are able to walk so much faster than the North American bots, because the North American bots are using classical control systems because they have to, because they have these highly geared actuators, whereas the Chinese bots are also down to like very low gear ratios, like 5 to 1 or something like that, because they're literally using like drone motors and other things. In some ways, it may have been over-engineered and over-thought through on what to do, whereas a lot of these other companies, maybe they didn't know better, and they just kind of grabbed some of these things that were out there that were kind of close that they could get in the supply chain and get faster, better results right away. And this is something that he points out in the spaces is a lot of times the best thing to do when going into something is to be completely naive and a dummy about the whole thing.
I saw that.
Part of the success of Tesla is the fact that they were not in Michigan, because they don't have the Michigan mentality when it comes to building a car. They made a lot of mistakes, but they also made a lot of innovations because they weren't locked into this mindset. So the gigacasting came out from the fact that, they said, why not? Whereas everyone in Detroit has been saying no for years and years and years. They weren't listening to that. And the spaces yesterday, it was pretty funny. John Carvin, he talked about how a lot of the classical roboticists were coming out and criticizing a lot of these humanoid bots and how it can't work, this and that. Where have we heard that before? Where the experts, they weigh in and they are just so off base. They have no idea what they're talking about. And that's why I made sure to tell him when he introduced me in the space, I said, I'm a classical roboticist. Please do not listen to us, because if, otherwise you're going to have an industrial robot in your home.
Yeah, exactly.
Because and I've seen a lot of the takes in the classical robots. It's like, gosh, you just don't get it. You really don't. You were thinking that way, and it's just like, what's the old adage in physics? Physics moves ahead one death at a time. It's like, because you get this is like, no, this is how it is. This is how it is. You're just kind of locked in, and you need that fresh thinking. So he was absolutely right. Sometimes the best thing is to go in, and that's part of the success of a lot of the other companies, is that they're not necessarily hiring the top talent, and that was actually part of the success of the Tesla bot program in the beginning. Is they didn't go out and recruit all the experts. They didn't recruit a hand expert. They didn't recruit a guy who's like an expert in walking or this and that. And from the behind the scenes that we saw in Walter Isaacson's book, you just kind of see it's like they had absolutely no idea what they're doing in the initial days of the design. And that was actually their huge advantage. They didn't know what they were doing, because they could experiment, they could think about it, and they could learn. And I actually had a professor at Cornell whose advice to graduate students were that when you begin a research project, do not do a literature survey.
Yes.
Do not. To go in, attack the problem from your own, Then as you get it, then start comparing what other people are doing in it. And then of course do the literature survey, because you're going to need it for your thesis, right? You need to have it for the bibliography. And it was kind of a shocking. It's just because the whole idea is that you're trying to innovate. You're not trying to copy other people. You really need to go through. You need a little background information, stuff like that, and you'll kind of get it. But the best thing is to behave that way. So Bernd continued down this thing, because if he listened to everyone else, they would not have done the tendon drives. They would not. He did not give up on that. He was persistent.
Right. And this I was freezing on this frame because he's in the middle of pushing on it to show how the tendons are very complex. Just by their nature, anything long and skinny is going to be stretchable. So it just gives you that advantage, which is a huge advantage for
it's the additional compliance
around people.
That you'd like to have in the system. Now, again, from the standpoint of classical roboticists, it's like, you got to get the compliance of this. How are we going to control this thing?
Right,
if it's got all this flexibility, compliance, it's really hard to model. There's no way we can get any accuracy and this and that. And it's like, well, we're meat bags, right?
Yeah,
we're very flexible.
Yeah, we're super compliant.
Our actuators go out of calibration every day. I mean, literally, when you wake up, you're almost having to recalibrate your whole system to figure out where they are. So, and we compensate for that really quickly because of these two eyes.
Right.
And so you got to remember,
and proprioception, of course.
There's a certain amount of proprioception, but remember, the proprioception comes down to the internal calibration model that you have.
Yeah.
And the fact that your proprioception is assuming a certain amount of strength in your muscles and flexibility in your tendons and everything else. And that constantly changes. So your proprioceptive system is constantly having to update.
Right.
And so there's always that sense of feedback that it gets there. And it could, this is one of those experiments you can do in the morning. I've done this famously. I keep on closing my eyes and touching my nose because my proprioception is working really well. It may not work that well when you wake up in the morning. Mm-hmm. If you try doing that in the morning, you might poke yourself in the eye. All right. So be careful.
Just be aware.
But, after you kind of go through is your whole system, because, your muscles are atrophying and stuff like that. Now, normally with a classical robot is like, the torques that your motors can produce, and they always produce the same thing. Yeah, they're going to degrade over time, but it's not going to be like they degrade really rapidly, overnight or something like that, or, after you've had a long flight or something like that. Yeah. So, you need to have a system that's able to adapt from it. And, clearly all these systems have to be able to do that, to be able to work.
Right.
And the main thing is that you can see what your actions are and how they're working. And you've got the proprioception gives you a good guess at what's going on, but it's not the final arbiter on whether you've actually accomplished the task.
Right. Yeah. And so, but again, it's the beauty of all of this stuff is, and the reason why classical roboticists like yourself, the reason why compliance had to be pulled out of the system was because the software was not adequate to operate something. Yeah. I love that. He's doing, there we go.
It's really, when it was first starting out, there was very simple models that you had for the robots, which are basically kinematics, and you tried throwing some dynamics on there. And it was already challenging because you would take these shortcuts and go right to where the joints are, and assuming your actuator is at a joint, but the actuator is never at the joint. It's somewhere else. It's going through gears. It's got other transmission systems that's going on there. And so to model it correctly, you have to do a lot. And this, has been able to be accomplished by the classical robotics using, classical controls. And it's just a tedious and hard thing. But they want to get as many of the variables out of it, and keeping things rigid and stiff as much as possible just makes it easier. And making it soft and flexible, just at some point you cannot solve it with classical means. And this is why, tendon drives would have been a failure 10 years ago, because you can't do it that way. You need an end-to-end approach. Absolutely. It's got to be a lot of machine learning, reinforcement learning, everything else to figure it out, to get, to understand what are the parameters of that particular embodiment. Could be huge challenges. I mean, the other things you have to overcome is trying to manufacture these things to be identical is going to be very, very hard. But it seems like they probably understand what those challenges are and what they have to do to compensate.
Right. Well, I think there's a couple of things. Number one, to give Bernd credit, EVANNEX was founded 10 years ago. I think it was 2014. So, so he's been working on this since before. This is kind of like Tesla, that visionary thing that Elon Musk said, hey, let's do autonomous driving, before it was at all clear, number one, how to do it, and number two, whether it was even possible. And so this tendon, the idea of tendon drives and having a very different method of creating a robot was not, nowadays it's like, oh yeah, we've got neural nets so we can do this. 2014, 2015, that was not obvious at all. It was
bold.
It was very bold.
It's like, it's almost insane to do it, because it seems like it's almost too early. You don't really have the AI that's there.
Right.
Your motor tech, he said at that point, motor technology was really bad because, EVs were just starting to come around, and there had been no improvements in that area. You might have been starting to see a little bit of improvement because drones are beginning to become popular.
Yeah.
And so you had a little bit of work on that. But for the most part, it's like you would look at it and say, oh, the technology is not there. Well, how does the technology get mature? Someone's going to decide to go ahead and start working on the problem. And so, yeah, you go in, you roll up your shirt sleeves and plug away. And then there's a lot of other improvements happening around you. I think he talked about the shift they made in 2022 to just go full end to end.
Yeah.
That, he said it's like one of the most important decisions of the company at that time to go ahead and say that's how we're going to solve the problem.
Yeah. And again, even at that time, fairly bold. I mean, it's not obvious that that's the solution, especially not a couple of years ago, although it was starting to become obvious. But it has huge impacts because of the nature of, the more we imitate biology, the more we imitate humans, the more compliant these things are going to be, the more variability there's going to be in them in terms of because you also want to get manufacturing costs low, which means that what am I looking for? The word. Anyway, from one to the next, they're not going to be identical as much because you're going to have
when have very little variance as possible. So it depends upon the materials and everything else you're using and how easy it is to have repeatability from one to the other. And whether, like you say, you're going to have a lot of variance in some, so they have to be within some tolerance. You can never have them absolutely identical. So your system has to be able to deal with that. And classical roboticists know how to do that, because we realized long ago is like we always had like the ideal picture in our heads of what our robot is, and then design our control systems around it, and then we're shocked when the robot is not as repeatable or as accurate as we want. Is this because you didn't actually build it to the design specs as hard as you tried? There's always that little error. And then once you figure that out and you build your second robot, it's like, my goodness, wait a minute, we're using the same parameters, why aren't they working? So because each robot has what's literally its own signature. So the solution is that you run the robot through a series of exercises and measure a lot of points in its workspace, and from it you basically do something like back propagation, figure out what actually the errors are in the system, what are the true joint offsets, the true lengths, the true errors at the joints and how they're mounted and everything else. And some of the parameters they can have with the joints go crazy. They have like up to 24 parameters per joint.
So and that's also a delta, right? You're measuring the delta. So you have your spreadsheet.
You're basically you're measuring the error, right?
Yeah. So you have your ideal table, and then you have another table that you kind of add or multiply to get the real one for that.
To say what's the the actual problem is. Yes. So what you end up doing, you say, I know this is how I'd like to go there. And what are the errors I have to, it could be as simple as that, you're assuming the arm, when it's in its home position, that this is a perfect 90 degrees, but it may turn out that, and that's your encoder 0 here. And then it might turn out that, well, you actually put a protractor up there, it's 89 degrees. Okay. So what that means is that every time we come up with our inverse kinematic solution, you just have to add a 1 to it, and then you'll get the ideal one you have. And then you do the same thing with a length. It turns out the length is not quite right, and it's like, if you know what the actual length is, then that can be part of your inverse kinematic solution to get what you want to have to be able to do it. And then your robots suddenly become swappable because they are repeatable. So if one robot breaks down, you can remove that bot, drop the next one in, and run the program you already had in there, and it will still work. That was always a problem in the early days, is they swap out the robots, and the new robot was way off from what they're expecting. Like, oh my goodness, what's going on? So calibration has been around for a long time. They're doing another form of calibration in there, and I've certainly, when I've listened to a lot of the presentations that you have, you can kind of hear the hints about the calibration has to happen. The same thing happens in FSD. You got to calibrate your cameras, right?
Yeah. And that takes time. So the individual ones,
and probably the same thing with the steering wheel and stuff like that. I mean, just the way it kind of turns, there's some parameters that you would like to pick up to know that if I need to make this kind of turn, then the inputs I'm going to have here are going to have to be a little bit different than what the ideal vehicle is.
And then of course that will change over time as well. With the car, as the car ages, that a lot of the
tire wear, everything else.
Exactly.
And then your road surfaces that you're on. So part of it is like a feedback loop that for the most part, you say, I know under ideal conditions, this is how much you need to turn the wheel. But however, I'm not getting the response I'm used to doing. So I need to kind of adjust that a little bit. And we do that as humans as well, because a lot of times we will suddenly sense hey, the car's not quite responding what I'm used to doing here. I need to do something a little bit different, to go a little bit, slower or something like that. Or I need to turn the wheel a bit more because my road surface is maybe a little more slippery or something.
Yeah. Well, I mean, we could take it to the extreme of like, I remember when I was young and had very, very old cars, and you kind of get used to the fact that you're actually driving like this to go straight, or that. No, but I'm saying like that the steering wheel angle would get off, and you're like, well, it's a positive 10 degrees, but we're actually going straight, right? So.
Well, the other thing is that you had steering wheels that were like that, and now newer steering wheels are a little bit tighter in there. So you go from one vehicle to another, you already have to get used to the fact that you've got something different. And then you're right, some of them are really sloppy.
Yeah.
And then there's just the other thing is that, everything about the car is different. So we pretty quickly adapt to that. Yeah. But we adapt to it just because we see the results of what's going on, and it's not doing what we want. So we compensate.
Yeah. So that's where the brain comes in. And that's where these newer bots have a huge advantage, because they're able to do end to end. Again, we've talked about this before, but in a classical sort of roboticist sort of manner, what you would want to do is separate out each joint and solve it by itself. The problem is that that's not the way that a humanoid bot can possibly work, because as you move your arm out, your center of gravity changes. I just watched myself. My body actually moved backwards so that I didn't like fall over when I put my arm out, So it's like all of these things they're not independent axes. They're all correlated.
They're static and dynamic. I mean, one is like, if I'm just holding my arm out there straight, I have to lean a little bit to keep myself from falling over the center of gravity. But as you're doing that, you're getting a reaction force as well. So, there's a dynamic problem as well. And depending on how fast you move, and that was something that I think Bernd was also talking about, the importance in teleoperation. Teleoperation is very difficult because of the lag. You're not seeing the same thing and all that. And so you end up being a bit slower when you're telerobotically doing stuff, just because you don't have enough confidence in the system, the feedback. And he says that the thing is, physics doesn't turn off or slow down.
Right.
So, so the idea is that you want to get as close to real time in the teleoperation. Otherwise, the system is not really reacting correctly based on the physics it has. So if I'm picking up this bottle and moving it really slowly through there, it's very different than if I pick it up and move it quickly. Yeah. And so if you want to do it on like the normal rate you're going to go in there, you're going to have that, because everything is going to be different. You're now going from what's basically static physics to now dynamics, where now I've got the inertia of the system. Now I've got the resistance of that inertia. Everything else is going on, the sloshing, the bottle, all that's going to be very different whether you're going fast or whether you're going slow. So the teleoperation must be as close to real-time speed as possible. And that means you have to focus an awful lot on how do you make it have no lag, really rapid response, and your field of view is really good. Because a lot of times the reason you're going so slow is you're not seeing it as well as you would like to.
Exactly. Well, and you don't have tactile feedback, so you go to pick something up teleoperatedly, and it's like, well, did I squeeze it hard enough or not? I don't know. So
now the bot has tactile. It's a question of how much haptic feedback you might be getting.
Yeah, well,
I'm
looking at
which is very different. Yeah. So you might be getting like it might be vibrating a little bit to kind of tell you what the contact, but it's very different than what you'd really be feeling the fingertips. So the bot's kind of picking that information out, because it is key. Bernd referred to that they do have tactile, but it's not as good as he would like it to be. Because if you remember, Robert Scoble asked the classic question of like, can it throw a football? Can it play catch? He wants to know that. And it's like, it's got this, the speed and the strength and everything to be able to do it. It just probably doesn't have quite the touch that you have to be like Tom Brady. Okay. It's like, as far as, it could probably throw a pass about as well as I can, which is not very good. Maybe it can get the spiral in there or something like that.
I don't know. So I'm not sure that they can do any of that yet, but anyway, but that's a goal.
It'll, be, it'd be kind of interesting if it can go. I mean, I'm sure it can lob it a little bit, get on. The question is, like he was saying, is just kind of knowing what the grip should feel like as you're going through there in that transition to get that really good pass in there. And so they have some tactility in there. It's just they need probably a little bit more. And, that's for future versions.
But I think that we should give them credit, EVANNEX, because of the speed. There are some robotics companies that have focused much more on doing things much more sedately. I mean, you watch the robots walk, you watch them move, they move at like kind of half human speed, but it sounds like EVANNEX has the capability to be able to do quick snapping motions. I mean, Unitree would be another one. So
we haven't seen it yet. We've seen these baby steps.
Yeah,
they're just starting to do it. The expectation is that by the end of the year, the walking speed will be 2.5 miles per hour, which is great. It's right where you want it to be for most tasks, especially in the household. And it will be able to run at about 7.5 miles per hour, which is pretty good. And we'll be able to jump. Whether it can do backflips, that's something else. But given the fact that it's only 5'5", and 30 kilograms, or about 66 pounds, that's like a very light gymnast. And I would think you would be able to do a backflip if you want to, especially if it has, the kind of torque, because the strength to weight ratio of this bot's incredible. So he said it can do, a squat or deadlift of 70 kilograms.
Right.
And that means first the hands actually have to be able to combine, be able to hold that amount of weight.
Which is a lot.
And it's more than twice its body weight, which is remarkable. So it's what I think about 150 pounds or so. Now normal carrying is about, I think, 45. So that's, which is also not bad. That's about the limit of your carry-on luggage. Not your carry of
45
check baggage.
No,
check baggage is 50 pounds.
Yeah, but did he say 45 pounds or 45 kilos? That's the question. I don't recall.
I thought it was 45. If it's 45 kilos, that's a lot. Okay. I'm mixing my units because I keep on seeing. But I think so. It can deadlift. It can deadlift 70, but I think carrying maybe it's 40, because that's about what everyone else is like, kind of in that order. You don't need to be much more, because you really think about what the OSHA limits are, and that's about where OSHA puts it. That's why the airlines have capped it at 50 pounds, because it's been the decision that once you go above that, you're actually talking about potential worker injury, and why you have to pay a bit more. So the workers, it's like, okay, this is a heavier bag, we have to take care of it.
Right. And maybe have 2 people lift it or something like that. So
to lift it or some other way. Yeah.
Oh gosh, I had just thought of another good question for you, but I guess we could actually turn to the comments at this point too and see what people have asked since
sure
live stream. We can do that. You're welcome to look through too. I saw someone, I can't remember who it was, sorry folks, but somebody said, well, I get it. They said yes. So there you go. Does Scott think the hands-on Neo are similar to what Tesla is planning on doing with the Optimus, where the actuators are in the arm? I think we answered that. That was early on in the conversation. So
yeah. So for anyone that didn't hear that already, for the most part, this is a preview of what I think the Tesla Bot 22-degree freedom hand will look like.
Right.
It will probably be very, very, very similar, and we'll see what they have to do to kind of match it. This has 1 extra degree of freedom, so this is really a 23-degree freedom hand. But everything is down the forearm. Maybe the same number of actuators, maybe not. We don't know about, again, can it do the Vulcan salute or not, or just this, which we're pretty sure. And the other unknown is whether the finger links are going to be different. And again, all this stuff is that we haven't been told this directly by Tesla. We're just kind of intuiting it based on the number of degrees of freedom. It means, they have to be adding a knuckle in for each of them, going from 2 to 3. This movement here, with the talk with Lex Friedman, and the importance of the pinky and stuff like that, was kind of an indicator to me that there's probably thinking of having individual finger links and everything else. And of course they should have a very thin, because of that, their palm will be much thinner again. So I would think it's going to be pretty close, very similar in design.
I think, and Ahsoka, this is actually, we forgot to point this out, but he was like, this isn't like a gimmick having it in the household, but I don't think it is, because of the way that Bernd is talking about this. Now I know most people are like, factory first. This is where the money is. This is where you can lease it. You can make a lot of money off your bots. But Bernd's counter argument to that is that the unstructured environment of consumers, just like us drivers, think about if you only had full self-driving being trained by UPS drivers or something, right? That will give you some data, but it's not going to give you all the data. The best data is to have everybody be able to drive and have the massive range of experience. So that is his take on that.
And which we've seen, FSD works great in California, but not so well outside. The regional differences for some reason. So we need to point out, this is the S3 podcast from Jason Carman, and this is an 18-minute documentary about it. And there's a great interview in there with Zhang. who talks about that and the importance of having a breadth of data.
Yes.
And that whereas be very narrowly focused. If we want to use the analogy, it's just like, Tesla's FSD, the idea is that we are driving everywhere, we're getting the data there. Whereas, Waymo and Cruise like, oh, we're just going to be in San Francisco, and we're going to try to do it that in a very geofence kind of thing.
Right.
And the arguments of like, well, we see that the downside of it. The other thing I've kind of pointed out is the importance of cross training. Every single athlete does a certain amount of cross training because to become better at what they want to do, they do something else which is completely unrelated to what they have. Right down to the point that Bobby Fischer, who was a chess champion, he was a big proponent of jogging, going out and getting exercise and stamina of something completely different. So these things do feed in, even if they seem to be orthogonal to one another. And again, that, they feel that going from the home into the factory will be a lot easier than going from the factory on in. Not to say that there is no economic advantage to being in the factory. But if they're able to get this, the strength and weight of this is absolutely remarkable. And everything else is that I don't necessarily see what the huge impediments would be to getting this in the factory. It may even go in there easier in some ways because it has a certification to work right next to other workers. So it's going to be quite interesting to see as this develops. And if you watch this documentary, you get an idea of the timelines they're talking about of when they start doing major scaling. But he did say that there is a limited beta program right now. I think they've got already most of the people. Unfortunately, just like with FSD, I'm not on that list.
I know. I was like, darn it.
Because and part of it is just everyone wants it, but they've only got so many units. I mean, FSD was a lot easier to give to everyone because it's just a question of copying. But they wanted the data first before like giving a broad release because they need to make sure it's really safe. Whereas, the problem here now is like they can only build so many. Now, I think he said that how many did they make last year? They were making maybe 10 a month or something like that on that order.
Right.
But he's saying that their expectation with Neo is that they will be able to go at a greater rate than what they did with Eve. So it could be that by the once they scale up, they can have a reasonable number. We're not talking about tens of thousands. But hundreds, potentially, low thousands or something like that within the next year, that maybe people would be able to get into that beta program, and at a price that should be on the order of purchasing a vehicle.
He said pleasantly surprised. He was not specific about it, but
not specific. My feeling is probably less than $100,000. Maybe even if he's really talking about not a luxury car, then he's probably talking less than 50. I mean, some people say, well, wait a minute, it's still a luxury car. The 25 is more like, so we'll see. So be pleasantly surprised.
There will be, no matter what the price, there will be a market for a small group of people because the early adopters will always be there. So, so I think that what we're seeing, there's a difference with, and Bert talked about this in the Spaces yesterday, that the advantage of building a robot like this is that the bar of having it be used around humans is so much lower than full self-driving. Because when you've got a 3,500-pound death machine that's driving 70 miles an hour, and remember the energy of the system, mass times velocity squared, that is just, you're just pedaling death at that point. I mean, that thing is a barreling huge kinetic energy transfer thing. So you have to be incredibly careful about deploying your software that it works perfectly. And here you don't have to be quite that careful because the bot, he said if you run into it straight on, it's going to hurt like you're playing football without pads on. And it's like, not something you're going to want to repeat a lot, but it's not going to, injure you terribly or kill you or something. Whereas a car,
and it's also going to absorb a lot of the energy. So again, that you bump into it, the joints and everything are going to suddenly spring back and stuff like that, and absorb a lot of that energy of impact. And everyone kind of falls down the ground, it's like a little bit shaken. But it's and the other thing is there's no sharp point on here that could impale you or hurt you when you run into it. So the whole idea is that everything is soft, everything is rounded, no hard sharp edges or anything like that. That you would not. I don't see this as being something that's going to be very dangerous in the house. I mean, the biggest disaster would be that someone loses its balance next to the china cabinet, and the china cabinet.
That would suck.
And that's probably going to happen. It's just, it's the nature of it. But even then, you might be pleasantly surprised that I'm pretty sure that if this thing powers off or something like that, I think it goes very limp.
Yeah.
Which would be typical for a lot of these back. And that's like one question I'm going to have for him is that when it's just standing there doing nothing, I think it has to consume a certain amount of power. You have to be providing some torques in all the joints for everything to be able to sort of stay where they are. You just can't stand there for free without expending a little bit of energy. And but that means when you turn it off, and we've seen that with like agility, that they had something happen with Digit was going over there, and it just kind of collapsed because it's like the power just went out. And once that happens, that's all it's going to do is kind of go down. So it's going to fall like a sack of potatoes for the most part. And there's some images in there of it, hanging up there on the chassis while they're doing some work on it. And you can just kind of see it's like whoop, all over. Now, the other thing I do like about it is that right around where would be kind of the belly button. They have like motion there in the torso. So it can really lean forward quite well, quite compactly. So it should be able to like sit down in a car. The other thing that's really impressive, and we did have an image from behind, and we've seen some of the others, is I don't know how to put this politely, but when I kind of looked at it, all I could say is, man, nice ass. Is that it's just unbelievable what it's not like Optimus where you have these two big motors sticking out, and all the other ones that we've seen is that you don't want them sitting on the sofa or anything like that because it's just going to tear the thing to pieces. You don't want it in your car because your nice vegan leather, that's going to be the last you see of that. So they really designed it. It's just unbelievable what it's like around there, and that and how they made that design based on really trying to imitate the humans. So overall, it just seems that it's got that factor. Now, again, we've sort of talked about, do you want to have these crazy range of motions and be able to do, hyper extension, stuff like that, all that. And you see, I think at the Shanghai show, they were showing some of the shiny spots that are similar to the Atlas, the new Atlas from Boston Dynamics, where they could just put the arm out and like spin the shoulder joints back and forth and like that. Okay, it's really cool. What you're demonstrating actually is textbook singularity. That's the reason why you can get away with that. And we really don't like that in the robot community, at least the classical guys. We hate that. And I don't see the utility of that. So you design something that has a capability you don't really need, and you're trying to push it as a positive. I see it more as like a negative. And they show it on the couch and like just being able to like turn itself under pretzel and all that stuff. Like, I guess it's kind of neat to be able to put it into a little suitcase and mail it off somewhere if I want. But for the most part, you don't need that degree of flexibility. It's more of a party trick than anything else. And here it seems to have enough. And again, making sure that, the whole pelvic area, the buttocks and everything is just normal as far as a human form, being able to sit anywhere, not going to bump into things, not going to cause any sort of injury, just a remarkable design.
Yeah. And I have this screen capture or the still frame here that, you can see how he's able to bend over pretty far and pick up a backpack.
And you can see a little bit in the torso as well.
And also, by the way, everyone should be impressed by this motion because teleoperated or not, the balance point changes pretty drastically as it picks up the backpack, because all of a sudden you've got 10 extra pounds or whatever of weight as you're bent over. There's a lot of balancing that has to happen as it does that and lifts it out to her. Now, it may be super, super light. Maybe it's only a pound or two or something like that, but still it's got some weight in it because you can see that the backpack, it's not floating. It's not a balloon. So, it's very impressive that it's able to do things like that. So I want to be able to, let's see, I was trying to look at, by the way, Robert Hirsch, go Dogs. That was a great game yesterday, by the way. UGA Clemson game. And apparently he went to UGA as well. So anyway, cool stuff. And let's see if I don't know if you saw anything else. This is interesting. Dot says robots will never be as good as humans everywhere. That's an interesting comment. I think that what we're going to find is similar to Deep Blue beating Kasparov in chess. I think that we will find that there's no question that a computer is way smarter than a human in chess, and we will never ever there's no way humans could ever compete with AI in chess, and we don't care. We just like to play each other in chess. It's like it's pretty boring. You don't really want to watch two computers play chess against each other. So I think robots. I'm coming up with a more optimistic way of looking at this. Robots are going to be critically important to the world. They're going to increase our labor pool, but the things that really matter to us are going to be human still. So that, it might be a renaissance of artists and artisans now, because it'll be like, yeah, okay, fine. We can have a very nice Hasselblad quality camera that a robot can build for like $20 eventually, but that we'll want to have one that a person actually made, just because that's cool. So,
And the other thing is that it could help out in so many other ways, like population decline. Everyone's afraid, once we have these things, there's going to be no incentive for people to have families. It's like, it may be the opposite, because the reason why people either don't have kids or have a small number of kids is that the amount of societal pressures and everything else you've got to try to do becomes really, really hard to provide everything that you want. And now you've got something, just childcare is ridiculous. I mean, people should actually look at how much it costs for preschool, because you look at it, it's like it costs almost like the same as sending your kid to college, and they're only like 3 or 4 years old. And the thing is, and because you look at it weekly, and remember, you got to pay for them in the summertime as well. Not just during the, so it can get pretty expensive. So, having something like that, and then it's like, oh, but we don't want our kids raised by the bot. So it doesn't mean that it's going to be raised by the bot. What will happen is that when you come home from work or something like that, there are chores you have to get done around the house, right? Which is what limits the amount of time you can spend with your kids. Now suddenly it's like, let the robot take care of that. Now let me play with my kids. So it's like, well, the robot might be able to do there to take care of some things. The reality is, it means you'll have more quality time with your family and with your kids. And then you'll say, hey, it might be fun to have a couple more of these around there, because the robot is just acting more or less like a governess. Everyone's basically going to have Mary Poppins in their house now.
Potentially, eventually, a relatively cheap Mary Poppins too. So I think one of the big problems that, that's, I stopped it. I have 4 children, but 2 of them are adopted, but I stopped at 2 biological children, because I was like, whoa, we're looking at $200,000 a person to raise them from infancy to, 18 years old and plus college. It's like, that's expensive. And it's like, if you could order of magnitude that cheaper, then it's like, well, okay. I
think it'd make a pretty big change, because you might suddenly go from, with everything else, as you start to get this age of abundance, maybe you no longer need to have two earners in the household. In many cases, that's the reason why you need to have childcare, because you both need to get a wage. And of course, and it turns out that that one of those wages almost just exclusively goes to paying for someone who's not a family member to raise your kids, right?
Which is a weird situation.
It's like, either way, it's like, it's not being raised by the parents, but by doing this way, you may actually have the parents more involved in the raising of their kids. So, it can cut both ways. It really just comes down to how people decide to use this. And, most people, they really want to have kids because they want to be with the kids as much as possible. And having to go to work is a necessary evil you have to do, so you can provide for them, so you can spend some time with them. But if there is some way to be able to reduce that burden, you'd be able to spend a lot more time, and it would be way more quality time, because maybe you wouldn't be as exhausted coming home from work and everything else. Especially, that's where FSD, I think, will help out, is that you won't come back because you're really cranky about the commute. It's just like, I'm all fresh, ready to go, and that drive home, will take care of all this other stuff I had to do, because I didn't have to worry about driving.
True.
So I can see a lot of these things here is making it a lot easier for people to have a much better family experience.
Right. Yeah. And personal one as well. Whether or not you choose to have children, anything that we can do to get rid of the drudgery of life. Like, a lot of yesterday was spent driving to Atlanta and back again, and we managed to catch football traffic coming out of the game because we left Ikea at exactly the wrong moment. But we had the car, which was able to do the full self-driving. Then I came home and did 3 loads of laundry last night while we put together some Ikea furniture. And that's old technology, but that used to require a person or people to do the laundry, and now it's just like throw it in a box and push a button and it just does it.
Right. So,
and
but then there's still the problem, the folding.
Yeah, you got to fold it and put it in the dryer and blah blah blah.
And those are like nice things that kind of like chores to do around the house with your kids. Kids. I mean, that's part of raising the family, getting to do that. But at some point, it becomes drudgery. The kids aren't really interested in that. Yeah. You really don't want to. Like, I want to go and throw the football with my kid. Rather than say, oh yeah, I can't throw the football right now because I got laundry to do.
Yeah.
Now with the IKEA furniture, you can either have the bot put the IKEA furniture together, or that's a really good family experience as well. I mean, say, all right, everyone come on down here. I mean, think about it. I mean, that's a kind of a bonding experience you want to go through, because then everyone can make the jokes about how difficult it is to put the IKEA furniture together. So if you want to understand all those social media postings about it and those references in movies, you got to build a piece of it once.
Yeah. And I think I still go back. I think we talked about this maybe even 2 years ago, that the IKEA test is going to be the ultimate test for a bot. And we're actually finally getting to a point where I think with these 20-degree plus degree of freedom hands and the intelligence they have, that we could eventually, not that far in the future, have these bots be able to look at the IKEA like diagrams, figure out what parts they need, and have the dexterity to actually build an IKEA furniture. And when they can do that, I will consider that a pretty solid robot Turing test, because it takes some human thought and ingenuity to be able to build those things too. So yeah, that's pretty cool.
Yeah, especially when there's only pictures, and you have to understand exactly, the little guy there with the wrench, and you're like, whoa, wait a minute, what's going on here?
Yeah,
because rather than putting it in 162 languages, which would just take up too much space, they just decide, nope, we're just going to use pictograms and that's it.
Yeah. And I mean, go them for making it doable, but it does it requires some mental gymnastics to figure it out. So I like Matt Senko here said humanoid robots with washing boards as an idea. Like, imagine them like,
oh yeah, if people want to know what it was really like, down at the river in the cold water and stuff like that. Yeah,
exactly.
Yeah, so yeah, those we have a lot of these labor saving devices, and despite the fact we have this labor saving, we still complain about doing the laundry.
Yeah, exactly. Well, but there's also the mowing of the lawn and yard care, and there's just a lot of stuff that these robots, just maybe 1 to 2 hours a day, probably for a household need, that would probably be adequate. So honestly, let's say there were $50,000 and you got together with 2 of your neighbors and had the bot go from house to house during the day while you're gone, and you split the cost, it wouldn't be that much money. So
exactly. And again, that's why they talk about that, the charging cycle and everything else. They only need to get about 2 hours out of it. Before it recharges, they go on to another task. So there will be definitely a lot of downtime where it'll be able to do experimentation, everything else, as was pointed out.
Yeah, exactly.
Now speaking of the FSD, were you on hardware 4 or hardware 3?
I re-upped our subscription on our Black Model 3, which has hardware 3. So I've been only using hardware 4, have not tried it. I'm actually going to do a video maybe for tomorrow to actually drive around with the new version and see how it compares.
It's going to be interesting. I'm definitely seeing a lot of people saying the experience in hardware 3 is not good. It seems to have a huge regression to what they're used to with 12.3.6 or 12.4. But everyone with hardware 4 is raving. It's like it's absolutely great.
Oh, it's great.
But in many cases, so it'd be interesting to see your take. I think Bradford did a test, and he was like also like a little bit not so sure. He's making a video of the comparison between the two.
Gotcha. Okay. Well, everyone look forward to that, and because that'll come out within the next day or two, because I just re-upped the subscription. But I think we have talked it out. We've been going for an hour and 20 plus now at this point. So thank you so much, Scott, and thank you to everybody who has been posting and everything. I'll tell you this. My kids, because they're so obsessed with pickleball, I actually want to see one of these bots play pickleball. I think it would be easier for it not to run around, but to hit the ball than throwing a football, because you grip the racket and you don't have to like let it go. So I think it would be easier for it to hit a paddle to a ball than to throw a ball.
There's plenty of ping pong playing industrial bots.
Yeah, exactly.
It's all for over 10 years or longer than that. Probably the thing I want to know is whether the bot will have as much difficulty understanding the rules as I do.
Yeah,
I still don't quite get what's going on. You know, when you're allowed to be in the kitchen and not in the kitchen,
right.
and where it's just all that forward motion stuff that I think you hit it. I mean, are you allowed to ever end up in the kitchen? I mean, I know your foot can't be in there when you hit.
No, but you can't have your momentum can't carry you in there either. But if the ball bounces,
even your momentum can't.
Yeah, yeah. So that's a problem because you'll hit it and then you'll be like, you're trying to stop yourself from like falling in.
So. You're trying to stop momentum and all the other stuff, and then like how many times it has to go over, and when you're allowed to hit it out of the air.
Right.
Okay.
Yeah. So anyway,
I guess I mean the actual scoring is fairly straightforward compared to like tennis, where you're still like, wait a minute, I don't understand this. Why they count in such a weird way? 15, 20. It's like, and then love for zero. It's like it's a very confusing way. At least pickleball, they say we'll make it like a table tennis or ping pong very easily.
Yeah.
But then we'll make the rest of the rules like so convoluted of when you're allowed to do this and that. And you got to count the things going back and forth before you can. Okay.
Yeah. Everything.
And then you get Canadian singles, and that gets even more confusing.
Yeah, yeah. I've played that with my kids, and they hate that because they're like, we don't want to hit on one side of the court, and I'm like, I'm too old to recover the whole thing, so shut up.
Yeah. So, yeah, exactly. So that's something else. And well, I guess part of the reason why I think they have exclusions on the kitchen is that the first time I played pickleball, I got one like right in the middle of the eye, like right in the bridge of the nose. And I was playing for it. And I wasn't in the kitchen, but still like, man, if I was.
Yeah, exactly. Well, plus the fact if you get up there, if you're like right on top of the net and somebody hits any kind of ball, there's no way you can get it back. So there's a reason why they do that.
Not only hit back, but just like get out of the way.
Exactly.
I couldn't move past, because you got to remember it's kind of it's sort of a wiffle ball.
Yeah.
So,
but it's pretty hard.
Depending on how it's not, it can be like a knuckleball, and like you think you know where it's going, like you're trying to move your head, and it turns out you're actually moving it into the path rather than out of the way, because it does one of those things.
Yeah. It's pretty good stuff. All right, cool. Well, thank you so much, Scott. And let us know, folks who watch this not live, what you think about all of this stuff. We will I don't know, just stay tuned to this space. Maybe we'll have some more cool stuff to talk about soon. I just reached out to someone today, so we will see if we have any more announcements on that space. So in the meantime, everybody have a lovely Labor Day for those who are in the U.S. and for those who are outside the U.S. Have a great weekend. All right, we will talk to you later, folks. Peace.
Bye.